everyone! In this video I want to discuss the 4 problems that 3b1b's left at the end of his recent video on an innocent enumeration problem, which I highly recommend watching, by the way. I do a lot with generating functions in my mathematical life, and so I thought it would be a fun idea to discuss these problems from my point of view. And I'll also throw in some bonus material on top. Let me mention, in case you like reading more than watching, I have produced an article about this in my blog. I'll leave a link to it in the video description. Before we jump into the problems, let me recommend some more literature. Aside from Herbert Wilf's generating functionology, which Grant already recommended in his video, I would also like to add the book Concrete Mathematics by Graham, Knuth and Petashnik, because I really like the way how the book is written in general, as well as their approach to introducing generating functions in particular. And if you would like to see how the theory around generating functions can be developed further in a more analytical direction, then I also want to recommend my favorite advanced book on the topic, the Purple Bible called Analytic Combinatorics by Flageolet and Sedgwick. If there is interest, let me know in the YouTube comments down below. I'll talk a bit more about the very powerful systematic approach to counting with generating functions described in there in a future video. Now with that out of the way, let's look at the 4 problems one by one. Problem number 1 is about a generating function and a die. The statement is as follows. Take the derivative of both sides of 1 over 1 minus x equals the sum over all n greater equals 0 of x to the power of n, which is 1 plus x squared plus x cubed and so on and so forth. And then we should use this information somehow to compute the expected number of times you have to roll a fair 6-sided die before seeing the number 1. The instructions from the first part of the problem are a bit clearer if we take a look at the second part of the problem first. This is because then we have an idea of what to look out for when we take the derivative on both sides. To determine the expected number of times we have to roll the die until we see a 1, we need to think about probabilities. We have a probability of 1 over 6 to roll 1 with our first throw, in which case we had to wait for 0 throws before. Otherwise we rolled a non-1, which happened with a probability of 5/6, and now we have to roll the die again. With a probability of 1 over 6, we rolled a 1 in our second attempt, which means we had to wait for 1 throw before, and with a probability of 5 over 6, we again failed to get 1. And so on and so forth. With the help of this state diagram, we can see that the probability for having to throw the die n times before we see the first one is 5 over 6 to the power of n times 1 over 6. Because every roll of a non-1 contributes a factor of 5 over 6, and the final roll of 1 contributes the remaining 1 over 6. Now that we have the probabilities, how do we get to the expected value from there? Well, we sum over all possible events, meaning 0 rolls before, 1 roll before, 2 rolls before, and so on and so forth, and multiply the number of times we had to wait with the corresponding probability. The sum we want to evaluate, therefore, is 0 times 1 over 6, plus 1 times waiting times 5 over 6 times 1 over 6, plus 2 times waiting times 5 over 6 squared times 1 over 6, plus and so on and so forth. And if we want to write it in short summation notation, this would be the sum over all n greater equals 0, n times 1 over 6 times 5 over 6 to the power of n. And we can actually also pull out the factor of 1 over 6 out of the sum. With that, we have a nice summatory formula for our expected value. This is as far as we can get at this point. Let us now turn to the more mechanical part of the problem, and then we'll see how to combine the two. Before we just go and take derivatives, let me add some bonus content though. The identity you're seeing is a rather well-known one. The sum on the right is the so-called geometric series, and from an analytic point of view, the identity holds for all real or even complex x with an absolute value less than 1. This identity can be derived directly, and let us take a look how this is done. We use an auxiliary variable, Sn, which denotes the geometric sum of the terms from 1 to x to the n. This 1 plus x squared plus and so on and so forth until you reach x to the n. We write this down and then multiply both sides with minus x, so that we find minus x times Sn equals minus x squared, minus x cubed, minus and so on and so forth, minus x to the n, minus x to the n plus 1. And now you might already be able to guess what we do next. The right-hand sides of these two equations are almost screaming for us to sum them up due to all of the cancellations. Indeed, by doing that, we get the equation Sn minus xSn equals 1 minus x to the power of n plus 1. If we factor out Sn on the left-hand side, we are left with Sn times 1 minus x equals 1 minus x to the n plus 1. Or as long as x is not equal to 1 exactly, we can also divide by 1 minus x and gain an explicit expression for the sum, namely Sn equals 1 minus x to the n plus 1 over 1 minus x. If we consider what happens when n grows large, this tends to infinity, then as long as the absolute value of x is less than 1, the term x to the n plus 1 will tend to 0. Everything else on the right-hand side does not depend on n, and this proves the identity that we've seen before for the geometric series. 1 plus x squared plus x cubed and so on and so forth, infinite series on the left-hand side, equals 1 over 1 minus x. Great, so now that we have proved our identity, we can go and take the derivative. But before that, one technical thing to note. Given that we are differentiating an identity, which means something that holds in an entire neighborhood, in this case of x equals 0, and not just for one particular value of x, we are allowed to take the derivative on both sides and we will obtain a valid equation again. For the left-hand side, I rewrite the fraction as power, then use the power rule and the chain rule to get minus 1 times 1 minus x to the minus 2 times minus 1, which we can rewrite as 1 over 1 minus x squared. For the right-hand side, we move the derivative inside of the sum and then use the power rule to arrive at the sum over all n greater equals 0 of n times x to the n minus 1. Combining the two sides then gives the useful identity 1 over 1 minus x squared equals the sum over all n greater equals 0 n times x to the n minus 1, which looks unsurprisingly familiar. If we go further and multiply both sides with x again, we arrive at x over 1 minus x squared equals the sum over all n greater equals 0 n times x to the n. Now if we go back to the sum we had found for our expected value, 1 over 6 times the sum of n greater equals 0 n times 5 over 6 to the n, then we can use the identity we've just proved to evaluate the series. We set x equal to 5 over 6 and find that the expected value is 1 over 6 times 5 over 6 over 1 minus 5 over 6 squared, which you can check that evaluates to 1 over 6 times 30, which is 5. Therefore, there are 5 expected throws before we roll a 1 for the first time with a fair die. Final note before we move on, the probability distribution that the number of throws before we hit 1 follows is the so-called geometric distribution, which is named like that because its probabilities form a so-called geometric sequence. The second problem is about the binomial sum. We are asked to compute the sum from k equals 0 to n of n choose k times 2 to the k. This is a problem that I personally like a lot, and I will share some bonus material about it after discussing the intended solution with generating functions. To solve this, we make use of the binomial theorem, which states that for any non-negative integers n and numbers a and b, we have that a plus b to the power of n equals the sum of k equals 0 to n of n choose k times a to the k times b to the n minus k. Observe that if we set a equal to x and b equal to 1, that we have the more specific identity x plus 1 to the n equals the sum of k equals 0 to n of n choose k times x to the k. The right hand side here already resembles the sum from the problem statement a lot, and in fact all that remains to be done is to set x equal to 2, and the equation reads from right to left the sum of k equals 0 to n of n choose k times 2 to the k equals 2 plus 1 to the power of n, which is 3 to the n. And that's the value of the sum that we've been looking for. I don't want to stop here quite yet with this problem. As I've mentioned, this is something I particularly like, and I do want to explain why that is. Identities like these are usually also an invitation to think about a more direct combinatorial explanation. And for this one, it's not too hard to find one. both sides of the equation that we have express the number of possible colorings of the numbers from 1 to n with 3 colors, say for example red, green and blue. To arrive at the left-hand side, 3 to the n, we go through all of the numbers one by one and pick one of the 3 possible colors for each of them. There are n numbers with 3 choices each, and therefore there are 3 to the n possible choices in total. To obtain the right-hand side with the sum and the binomial coefficient, we first decide that k of the numbers should either be red or green. So we choose these k numbers in one of the n choose k possible ways. The remaining n minus k numbers that were not chosen initially, we color those blue. And then decide in a separate step whether it will be red or green. There are 2 choices for each of the k selected numbers and therefore 2 to the k possible choices. For some specific k, we therefore find n choose k times 2 to the k possible colorings. And in order to obtain all possible colorings, we have to sum over all possible values of k from k equals 0 to k equals n. The fact that these 2 strategies with their corresponding counts both yield all possible colorings of the numbers from 1 to n with 3 colors proves that the identity holds. In combinatorics, this sort of argument is usually referred to as double counting. Now let's turn to problem number 3. Fibonacci numbers and a differential equation. Here's the statement. Let fn be the nth Fibonacci number and consider the generating function f of x is the sum over all n greater equals 0 fn times x to the n over n factorial. Explain why the differential equation f2 prime of x equals f prime of x plus f of x is true, and for bonus points, solve the equation and use it to find a closed form expression for fn. To find an explanation for the differential equation, we first investigate what happens if we differentiate the generating function of this particular shape. This is completely independent of fn being a Fibonacci number. A generating function with this particular shape of f of x, that is with the nth coefficient being normalized by n factorial, is called exponential generating function, in contrast to the ordinary generating functions that we've been working with so far. This is because the exponential function, as you might know, has the series expansion e to the x equals 1 plus 1 times x to the power of 1 over 1 factorial plus 1 times x to the power of 2 over 2 factorial plus 1 times x to the power of 3 over 3 factorial, and so on and so forth. In short, it's the sum over all n greater equals 0 of 1 times x to the n over n factorial. In other words, we could say that e to the x, the exponential function, is the exponential generating function of the constant 1 sequence. Here is how we determine the derivative of f of x. First, replace f of x by its series expansion, then distribute the derivative operator to every summand of the expansion. We then apply the power law to find 0 plus f1 plus f2 times 2 times x to the 2 minus 1 over 2 factorial plus f3 times x to the 3 minus 1 over 3 factorial plus f4 times 4 times x to the 4 minus 1 over 4 factorial, and so on and so forth. And if we recall that n factorial is the product of numbers from 1 to n and cancel its last factor against the factor we got from differentiating the monomial in the numerator, we find that this is actually f1 plus f2 times x to the 1 over 1 factorial plus f3 times x to the 2 over 2 factorial plus f4 times x to the 3 over 3 factorial, and so on and so forth. Notice that the coefficients are exactly shifted by 1. By rewriting the expanded sum in terms of sigma notation, we get the sum over n greater equals 0 of fn plus 1 times x to the n over n factorial. In other words, if f of x is the exponential generating function of the sequence f0, f1, f2, f3, and so on and so forth, then f prime, the derivative, is the exponential generating function of the shifted sequence f1, f2, f3, f4, and so on and so forth. And we can simply apply the same argument again to see that the second derivative then is the exponential generating function of f2, f3, f4, and so on and so forth. This is one of the most useful properties of exponential generating functions. Now back to our concrete situation where fn is the nth Fibonacci number. By using the corresponding Fibonacci recurrence, namely the next Fibonacci number is always the sum of the previous two, or symbolically fn plus 2 equals fn plus 1 plus fn, we can rewrite the second derivative of f as follows. First, we know from our exploration a moment ago that the second derivative is the exponential generating function of the sequence shifted by 2 steps. We can now use the recurrence to replace fn plus 2 with the sum fn plus 1 plus fn. And then expand the product and split the one sum into 2 separate ones. Both of them are familiar actually. The first one is the exponential generating function of the sequence shifted by 1 step, which is the first derivative as we know, and the second one is just f of x. So we can actually rewrite the right hand side as the derivative f prime of x plus f of x, which is the right hand side of the differential equation that we were asked to explain. In general, this is a problem for which generating functions are very useful for. And this is not particular to this specific example at all. Recurrences for sequences can often be translated into functional equations of their corresponding generating functions. And with a bit of luck, these equations can then be solved to give explicit formulas for the elements in the sequence. A very neat trick. Now, of course, we want to have full points, so let's solve the equation as well. Without going into too much detail why this works, we use the ansatz f of x equals e to the lambda x, which basically means that we assume that the solution has a certain shape, and you could say that we are just making an educated guess and then see how far we can take it. Plugging it into the differential equation and bringing everything to one side gives us lambda squared e to the lambda x minus lambda e to the lambda x minus e to the lambda x equals 0. We can factor out e to the lambda x on the left hand side of this equation, and because it's never 0, we may also conclude that our ansatz can only work if the equation lambda squared minus lambda minus 1 equals 0 is satisfied. And well, that's a quadratic equation. We can solve it to find two solutions, lambda plus equals 1 plus square root 5 over 2 and lambda minus equals 1 minus square root of 5 over 2. You can convince yourself that we actually just found some solutions to the differential equation. Both the function that maps x to e to the lambda plus x, as well as the function that maps x to e to the lambda minus x, satisfy the differential equation by construction. In fact, we can use these two solutions to construct the so-called general solution of the differential equation, which is a linear combination of the two. That is, some constant c plus times e to the lambda plus x plus some constant c minus times e to the lambda minus x. However, we are not looking for any solution to the differential equation, we are looking for a fairly specific one. The solution should, after all, be the generating function for Fibonacci numbers. To nail down the particular solution we are looking for, we have to use some information of the generating function. For example, that we want to have f evaluated at 0, which is the 0th coefficient of the sequence, should be 0 because it's the 0th Fibonacci number. And similarly for the derivative, we want to have that if we evaluate the derivative f prime at 0, then we should get the 0th term of the shifted sequence, which is f1, the first Fibonacci number, 1. If we take the first condition and plug it into the general solution, then this translates to the equation c plus c minus equals 0. So the two constants that we find have to cancel out if we sum them up. And on the other hand, if we take the derivative of the general solution and plug in the condition that it evaluated at 0 should be 1, we find the equation c plus times lambda plus c minus times lambda minus equals 1. Now we can express c minus as negative c plus from the first equation and then plug this into the second equation, factor out c plus, and we find c plus times lambda plus minus lambda minus equals 1. Equivalently, c plus can be expressed as 1 over lambda plus minus lambda minus. And a straightforward computation gives lambda plus minus lambda minus equals root 5, so that we arrive at c plus equals 1 over root 5 and c minus equals minus 1 over root 5. Now with both of our constants fixed, we have found the expression for our particular exponential generating function for the Fibonacci numbers. It is f of x equals 1 over root 5 times e to the lambda plus x minus 1 over root 5 times e to the lambda minus x. And from there, the explicit formula for fn is pretty much just the expansion of the exponential function into series away. Recall that the exponential function of lambda x expands as the sum over n greater equals 0 of lambda to the n times x to the n over n factorial. Then pulling together these two sums into one and factoring yields the sum of 1 over root 5 times lambda plus to the n minus lambda minus to the n times x to the n over n factorial. And from there, the coefficient fn can be read off directly. And if we plug in the particular values of lambda plus and lambda minus, we find fn equals 1 over root 5 times 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. Binet's explicit formula for the nth Fibonacci number. And here's the last problem. The statement is as follows. Suppose that f of x is the sum n greater equals 0 of a n x n, so the generating function of the sequence an. What do the coefficients of f of x over 1 minus x tell you? It invites us to prove a very useful sequence construction with many applications. For example, one can use this in the average case analysis of quicksort. And in case this has made you curious, let me know, I might discuss this in a future video. Here is how we can tackle this. We first rewrite f of x and replace it with its series representation. Then we multiply out and draw 1 over 1 minus x inside of the sum. We know, actually we've even seen it earlier in this video, that we can rewrite 1 over 1 minus x as the geometric series. Let's do so here too. If we then also draw x to the l into the expanded geometric series, we find the sum over all l greater equals 0 of al times x to the l plus x to the l plus 1 plus x to the l plus 2 plus x to the l plus 3 and so on and so forth. And this we can rewrite again in a more concise way using double summation as the sum over all l greater equals 0 of al times the sum over all n greater equal l of x to the n. While this double sum might seem a bit intimidating, we can also use a standard trick to try and make it look a little bit nicer again. We change the order of summation. Take a look at the diagram on the right. It visualizes the situation. Every dot in the diagram corresponds to one summand. The x-axis has L and the y-axis is N. In the original sum, we first iterate over all columns, which means L greater equals 0, in a way such that we sum over all cells above a certain threshold. If we change the order of summation, we first iterate over the rows, or n greater equals 0, and then over all dots up to a certain threshold, from say L equals 0 to L equals n. In a nutshell, we can visualize this as changing from vertical summation to horizontal summation. Practically, this means that we rewrite the double sum as a sum over n greater equals 0 of the sum of the coefficients a0 plus a1 plus a2 plus and so on and so forth up to an times x to the n. This is fairly hard to parse in formal summation notation, but makes more sense when we look at it in its expanded form. The series expansion of f of x over 1 minus x starts as a0 plus a0 plus a1 times x plus a0 plus a1 plus a2 times x squared plus a0 plus a1 plus a2 plus a3 times x cubed and so on and so forth. The pattern behind the coefficients of f of x over 1 minus x emerges cleanly. The nth coefficient is the sum of a0 to an, and so we can say that the generating function f of x over 1 minus x is the generating function of partial sums of the original sequence. And this concludes my discussion of the 4 problems. Let me know in the comments down below. Did you find this helpful? Are you curious about more generating function magic? Thank you very much for watching, and see you in the next one.